Hello, dear committee, ladies and gentlemen. My name is Volodymyr Kucharsky, and today I will present my current research work analyzing specifics of scalability laws for proper modeling of a system's throughput. In today's world, there are a vast number of artificial systems designed to make our lives easier, more efficient, more safe, more entertaining, etc. Most of them are designed with performance in mind, to meet the constantly growing demands of their users. The ability of a particular system to handle a growing amount of work or its potential to accommodate growth defines scalability. Scalability is crucial in system design for a few reasons. First reason, growth handling. A properly scalable product should handle the increasing number of users. Second reason, improved performance. A properly scalable product should degrade performance more gradually. Third reason, optimized costs. A properly scalable product should save business investment in hardware to operate according to the load. Unfortunately, in terms of combining computational power, 1 plus 1 doesn't equal 2. It could be some sort of cost-effective for batch work, but this combination was not effective for online transaction processing and other real-time computations. Jean M. Dahl made an early attempt to quantify the speedup factor, a number that shows how much additional performance a system will get by adding more computational units to that system to battle the increasing load. Here you can see the formulation of the law, where S is an actual speedup factor and P is a fraction which represents the parallelized portion of the work, and n is a number of computation units. Here in the slide, you can see how the amount of parallel work can be productive for a particular workload. Does this function has a limit? Yes, it does. It has its physical speed up limit and it's bound on the upper side to the fraction of 1 over 1 minus p. What can you see here? If we increase number of computational units infinitely and have only, for example, 5% of serial work, we will be limited on the upper side to the speed up factor of 20 because of that equation. So Neil Gunter proposed a slightly different approach to scalability quantification. His model not only uses the serial penalty, but also introduces a coherence or crosstalk penalty, which results in delays for data to become consistent during the execution of multiprocessor environments. How significant role does crosstalk delay have? It plays very significant role in the system's throughput because even a small fraction of that value can degrade your overall performance very significantly. As you can see, if we increase the number of total computational units to 128, we could achieve only at possible 9 the most effective speedup factor for this chart, and then we will see the gradual downscale of our effort. Another approach was proposed by Dr. John Gustafson to overcome the pessimistic results of Amdahl's law speed-up dependence from a serial delay. Instead of fixing the parallelizable part of the workload, it fixes the running time. In other words, it answers the following questions. How much the execution time would this problem have taken if it ran on a serial processor instead of multi-core processor system? So in here you can see in the top corner the totally sequential execution where the in blue is a serial fraction, and in pink you will see a parallel fraction which runs sequentially. And in the bottom side you can see the same execution, but on a parallel workload where every parallel fraction of the work is executed independently and simultaneously. Conclusion, all described laws have a potential for scalability quantification. Amdahl's law provides a straightforward to estimate the maximum achievable throughput by considering the proportional to the workload that can be parallelized, but completely ignores parallel crosstalk, which is inevitable in modern applications. Gustafson's law recognizes the potential adjusting the problem size to fully utilize the additional resources, which can lead to a higher system throughput in parallel environments. Universal scalability law accounts for saturation effects that may occur as a system resources are increased, providing insights into the maximum achievable throughput, but the diminishing returns the diminishing returns of adding more resources, more practical than the first two, but has a cost of additional complexity and more experienced researchers when determining the coefficients for an actual system. Thank you for your attention. This is all.